Thank you also to my nominators and to the Academy for the honour of being elected to its fellowship. Thank you to my colleagues, postdocs and students past and present. And last but certainly not least, thank you to my family for their support over many years of my scientific endeavours and pursuits. I work at the Australian National University. I'm based in the Centre for Gravitational Physics, which is in the Department of Quantum Science, in the Research School in Physics and Engineering. I'm actually a mathematical physicist, and I specialise in general relativity theory and gravitational wave science. So half of my research comprises the study of space-time singularities and its global structure, black holes and cosmology. But today, in this short talk, I'm going to talk to you about the other half of my work in gravitational wave science, because there has been some very exciting developments happened there recently, as I'm sure some of you are aware. I joined the LIGO scientific collaboration in 1998, and at that time I initiated activities in Australia in gravitational wave data analysis, and I've been developing those programs ever since. So the story begins, of course, with Albert Einstein's theory of general relativity in 1915, and this was a revolutionary theory which unifies the description of gravity as a geometric property of space and time. I've given the Einstein field equation there, and whilst I don't expect you all to understand it, basically the left-hand side of it encodes geometry of space-time, and the right-hand side encodes the mass, energy, and momentum of space-time. And so in this equation, Einstein puts those two things together in a very precise way. And in a sense, the right-hand side is a source of the gravitational field. The idea of general relativity is that matter warps or bends space-time. So a very famous saying by John Wheeler is that matter tells space-time how to curve. So if we place into space-time the Earth and its moon, then they will both dent space-time or curve it. Because the Earth is 81 times more massive than the moon, it will dent it much more. And on the other hand, space-time reacts back on matter, telling it how to move. So if we place a little satellite in between the Earth and the moon, then its motion will be dictated by the curvature of space-time. And it's this curvature of space-time that we experience as gravity. A big step, and this is one of two parallel paths going on in the years following Einstein's theory, was taken by Karl Schwarzschild in 1916. Now, Karl was an officer in the German army stationed on the Eastern Front in Russia when he performed this piece of work. But basically what he did was he solved the Einstein field equation for the gravitational vacuum field outside of a spherically symmetric star, which is depicted in the diagram there. And this was a very important early solution to the Einstein field equation. If you allow for stellar collapse, which is when a star uses up all its fuel and goes supernova and then collapses under its own self-gravitational attraction, then you can take the logical conclusion of Schwarzschild's solution and assume that it's vacuum all the way into the centre, so that only the very point, this singularity in the middle, has mass, and therefore it has infinite density. So that is the defining aspect of a black hole. The other important thing about it is the event horizon shown there, which is a one-way membrane. So inside the black hole, inside that event horizon, no matter, particles, electromagnetic radiation can actually escape outwards through that one-way membrane to the outside, because the gravitational pull of the black hole is so strong. And because nothing can escape, that's why it's called a black hole. The thing about black holes is that the general relativity community knew about these things for decades and were developing their understanding of them and looking at very important and general theorems predicting their existence in general relativity. But they were taken as quite a bit of a joke by the rest of the physics and astronomy community, who thought they were some kind of mathematical artifact or possibly an indication of a flaw in the theory. So it wasn't until around about 1972 that the first strong candidate for a black hole in Cygnus X1, which is in an X-ray binary system, was found. And this was many years after the GR community had started thinking about the concept of a black hole. So this was a great triumph for theoretical physics. The parallel stream I wanted to tell you about also started in 1916 through Einstein, and he published this paper in the Royal Prussian Academy of Science Proceedings from a mathematics and physics conference. And if you look at the date given here, it's 22nd of June 1916, which is almost 100 years to the day. And in this paper, he predicted a natural consequence of his theory was the existence of these things called gravitational waves. But he said, in any case one can think of, the gravitational wave amplitude will have a practically vanishing value. So he did not expect gravitational waves to be detectable, certainly in his lifetime and possibly forever. But in Einstein's lifetime, there were no lasers, transistors, quantum optics hadn't been developed, or pure mirrors. Gravitational waves are a very different kind of waves. They produce by wiggling masses, and these wiggling masses, they have to be in some kind of asymmetric configuration, and it can't be spherically symmetric. They produce these distortions or ripples of space-time which travel outwards from these disturbances of masses. And they also travel at the speed of light, but they are not light waves. But like light waves, they also have a range of wavelengths and frequencies. There is a gravitational wave spectrum, and different frequencies and wavelengths will be produced by different types of events out in the universe. Interesting point about them, they interact only very weakly with matter, and that makes them very difficult to detect. The advantage of them is that unlike electromagnetic radiation, they travel virtually unimpeded. So light is absorbed and scattered as it passes through the dust in galaxies, etc. But gravitational waves can travel to us directly from the centre of supernovae, from the centre of galaxies, and furthermore, we can look back to almost the beginning of time with them because the early universe was opaque to light, but not to gravitational waves. The LIGO detector story started 27 years ago with a proposal to the National Science Foundation, and today we have two of them based in the United States. They have 4-kilometre arm lengths and are shaped like an L. And basically a gravitational wave, if it passes through, will alternately stretch one arm and then the other. And by shining laser beams down each of the arms and interfering them, we'll get an interference pattern which is indicative of the gravitational wave. But during these 27 years, the theorists were very hard at work because we had to predict a type of signal that we were going to look for in these detectors should they ever become sensitive enough to hope to detect them. And the focus was on binary systems of 2 neutron stars or 2 black holes or one of each. And it took literally decades of investigation, both analytically by general relativists by hand, but also by numerical relativists to produce the breakthroughs that we needed to produce the waveform for such an event. This is Kip Thorne's diagram of a binary in-spiral. On the left, we have where the 2 black holes are orbiting, and they're still a long way apart, and we can calculate by hand, and it's very difficult and intricate, but we can calculate the expected waveform. And then they merge, and on the right, they form one black hole, which is all has lumps on it, it's wiggling around, but we have powerful theorems that tell us it has to settle down to a very spherically symmetric type of black hole, and so it gives off gravitational waves which we can calculate again analytically. The problem was the part in the middle where they're getting very close together before they smash together. That is very difficult. You can't calculate it by hand. We need to use the full Einstein equations, and we needed breakthroughs in the numerical code which were achieved in 2005. It's also the strongest part of the signal, therefore it's the part we most needed. That brings us to 14th of September, and I got a text that Australia has a new Prime Minister. So it was an exciting evening, but shortly afterwards, I got an email from within the collaboration saying there'd been a very interesting event in the LIGO detectors in the previous hour. And basically, we knew very quickly, within 2 or 3 hours, that we were looking at a binary black hole in-spiral system. And I'm now going to give you the sound of the event as it spreads across the universe from the 2 LIGO detectors. The first 2 passes are at the actual frequency, which is in our human audio range, and the next 2 are shifted up to our sweet spot of hearing, and you'll hear the chirp sound as the frequency goes up of the in-spiral. Okay, these are the 2 signals, and in the bottom diagram, they've been superimposed. There's a time delay of travel because the instruments are 3,000 kilometres apart, but you can see the 2 signals actually match very beautifully. Very extreme numbers. The collision event converted 3 solar masses into an energy burst equivalent of the total energy produced by 3,000 suns in their 10 billion year lifetimes. So it's in a huge burst of energy. It lasted only 0.1 seconds. And the rate of energy emission was 50 times bigger than from all the stars in the universe. But a person 10,000 kilometres away would only have been stretched by half a millimetre. The sensitivity was breathtaking of the instruments. It was equivalent to detecting a change in the distance to Alpha Centauri of 10% of the piece of the thickness of paper. And this is the simulation, numerical simulation of the black holes actually spiralling in their final stages, coalescing. The stars around the centre are sloshing around because they're in the background, their light is being bent around this spiralling system, and because the mass configurations are changing, their positions, as we see them, are actually sloshing around. And the black holes get very, very close till their horizons touch, and then they ring down very quickly to a very symmetric and beautiful black hole. This was our press conference, Parliament House, in February 2016, and that exhibits a number of my colleagues from ANU and also from around Australia. So just to summarise, this is the first direct detection of gravitational waves on Earth, the first direct detection of a binary black hole system, and indeed the first direct evidence of a black hole. It's the first observation of 2 black holes merging, and it was an open question as to whether they would do that within the lifetime of the universe. It's the first test of general relativity when the gravitational field is very strong and highly dynamical during the black hole merger. It has passed it beautifully. In fact, GR has passed it every test we've ever given it. The surprise was the size of the mass of the black holes was larger than that caused by gravitational collapse, according to our theories. So it is a question now that we're thinking about as to how did they both become so massive. And I'll leave this final slide up just to point out that we are now at the dawn of a new age of gravitational wave astronomy. And if you wish, in question time, I can tell you about the sort of things we might see. Thank you.
Thank you, Susan, for a very fascinating talk. Yeah, please.
Do we know anything about the location of the 2 black holes that was observed?
That's a very interesting question too, because our detectors just sit there and they don't tell us anything about the direction that the gravitational waves are coming in from. So you really need a network of them so you have a time difference and can triangulate and get a place in the sky where it came from. So with just 2 detectors operating at that time, we were able to pinpoint a portion of the sky of about 180 square degrees, which is not very small, as you know. But it looks like it was sort of in the direction of the Magellanic Cloud, and but much further away. But we're not sure.
A related question to that is, having seen one event, have you got a better idea of the frequency of similar observable events?
Yes, already with one event, that's been part of the first sort of work we've been doing. Subsequent to that is re-evaluating our estimates of the number of these types of events that are going to occur. And on the basis of this particular event, which did take us by surprise in many ways, we do expect to have a higher rate of these events occurring than we previously had thought.
Okay.
I imagine you would probably want to have a large baseline between your detectors. So would it make sense to build one in, say, I don't know, Australia?
Oh, that's the golden question. We've been actually trying to build one in Australia for decades, and it would be an ideal place because it gives us this beautiful tetrahedral effect around the planet. At the moment, there's one being built in Japan under 1,000 metres of granite, under a mountain, for seismic stability. Then there's also another LIGO detector currently being proposed for India. But yes, you're right. It would be fantastic to have one here.
Okay. Last question.
That merging of two black holes lead to some conventional signal that you could pick up as well as the gravitational wave?
There are no conventional signals expected from black holes merging. They do not emit classically in the electromagnetic spectrum. You know, it's possible that if you had something else going on nearby, you might see that being affected by it. But in general, we don't expect that. You know, classically, there is no other radiation from these black holes.
Okay, I think could you please join me to thank Susan for giving a fascinating talk?
Thank you.